I see
Hi,
a question
Professor.
from Mohammed. Yes, go ahead.
Hi, Professor. Thank you so much for your presentation. I have a quick question about the imaginary part of the density and the loss factor you defined. So normally I always think about the imaginary part of elastic modulus for the loss. So what is the difference between the imaginary part of density or the imaginary part of the speed of the sound compared to the imaginary part of the elastic modulus when we are talking about loss in the material?
Right. So the imaginary part of the sound speed is actually, well, it's kind of both. So the imaginary part of the density and the sound speed, when you combine them, you can actually convert it into the parameter of the index and also the impedance. And the imaginary part of the index is actually the loss. So it's kind of contributed by both of the effective parameter. Does that answer your question?
Yes, thank you.
You're welcome.
And I see Professor Nick Fang open his mic. Please go ahead, Nick.
All right, so great to see you and Mark in the seminar, and really enjoyed this inspiring discussion. So my question to you is, how do you compare the active gain or say this array that include feedback to the existing method of phase array? For example, arguably you could say that ultrasound transducers are already in the phase array. So why matters to add another, say, active matching layer?
Right. So in terms of the comparison is that nowadays people can actually achieve transcranial ultrasound by actually increase the amplitude and also like doing some kind of phase matching by actually use the time reversal method. So what we are trying to achieve here is we are trying to actually achieve an automatic matching of the skull such that you don't need to actually go ahead and then do all those kind of complicated time reversal and the matching, you simply just using the transducer itself.
So, sorry, along this line, how do you account for the interface modes? I see there are also some interface modes that are excited. How would you say go around or take into safety into consideration?
So in terms of the interface mode, what happens is we usually those interface modes are like having the high K components. So we can actually design a K space filtering to actually filtering all those like the interface mode. And also the other thing that we need to concern is the heating of the skull. So usually what happens is that because we have those like layers of the hydrogel, so what happens is we can actually use the metamaterial you designed to actually have the blast or have the water flowing through to actually bring the heat out in order to actually reduce the heating of the skull.
Okay, thank you. Chengzhi, I had one question on my side. One parameter that you don't discuss, maybe you've explored in the paper, I'm sure. But what about the thickness? Because I'm assuming, every time you see this impedance matching problem, one could say you could have not even like a complementary structure, just exactly the same, let's say, material properties as the skull, and just try to recreate like a Fabry-Perot condition to have like a multiple of blah blah by 4, and so you get like automatically impedance matching structure for one angle, obviously. But in your design, is this thickness, because you put the slab purple or green, but what about the thickness of this design?
Right. So the thickness of the metamaterial is very similar to the skull layer. The human skull is about 1 centimeter. So the thickness of our unit cell is about 1 centimeter, not exactly the same. The advantage of using the active metamaterial is we can actually virtually change the thickness of the metamaterial by changing the phase. So that's the way we use to actually virtually change the phase to adjust it and then match with the skull.
And you intend to have this unit cell really outside of the skull, obviously. Okay. Okay. Is there any other question from the audience. I see.
Hi, Professor.
Mr.
Professor Shi.
Mhm.
Can you hear me?
Yes.
Yeah.
In fact, I think high-frequency sound waves, especially those above 1,000 kHz, are greatly attenuated due to the existing of the score. So what can we do to overcome these problems, especially in the high-frequency ultrasound?
Right, that's what we are trying to do, right? So, yeah, you are right. For the high-frequency ultrasound, especially above 1 megahertz, the attenuation through the skull is very high. So we are trying to design this non-Hermitian complementary metamaterial to match the impedance as well as counteracting with the intrinsic loss in order to achieve this transcranial ultrasound. So now our goal is for the 1.5 megahertz, which is chosen because 1.5 megahertz is the one you will see in the hospital. Of course, in the lower resolution side. So typically in the hospital, what they use is about 1.5 megahertz for low resolution, and high resolution, they will use 7 megahertz. So we haven't reached that 7 megahertz yet. That will be future step.
Okay, thanks.
You're welcome.
I don't know if there's any on the. I'll take another one on the second part of your talk. I mean, it's brilliant idea. I missed a point. Maybe it was a bit fast, but you say at some point you plunge these two ultrasound in the clot, and you activate them, and you say you have a sort of scalar balance beneath, and you use this to make a reference, right?
Right.
I was wondering, like, because if you were measuring with the scale, like how heavily you push in the normal direction, I would expect that with the OAM, obviously this vertical push will be much less because you have much more tangential components, and such that when you want to have this axial component to be the same, you were actually using a lot more power in the OAM, and hence you have better results at some point. You know, I was just thinking, like, how does it compare if you compare with the with the power efficiency, if you take that into account? But maybe it's just because I'm new in this also in this way of looking at the results.
Yeah, in terms of energy, you are right, but it's interesting that we test the ultrasound power there, and they are at the same scale. Yeah, same level. Okay. Yeah, the same scale. And our hypothesis is that the reading of the scale, because the ultrasound transducer is not touching the, so it's not directly pushing it down. No, it's not. Yeah. Right. What results in that reading of the ultrasound scale is because of the ultrasound radiation force. Yeah. Right. And what we assume here is, in terms of the radiation force, doesn't matter which direction it is, it will result in a component which is downward. So they are not, the reading is not exactly the same, but they are at the same scale. Okay. Okay, interesting. Yeah, I think, Nick, you have a question?
Yeah, so it's a follow-up question. I'm wondering what is the size of the cavitation bubble compared to the vortex of ultrasound field, right? I was under impression that most of those cavitation models are assuming a radiosymmetric solution. So in other words, there was no angular momentum involved for the collapsing of bubble. But it seems like you have a impressively high efficiency of generating and radiating the bubbles. So I'm wondering if you had any thoughts about that.
Yeah, very good question. At the beginning, we didn't know what happens. We didn't know what happens until we actually go ahead and then search the literature, not in acoustics, but in fluid mechanics. So there are actually studies, very interestingly, they are trying to study like how bubble deforms when you have shear flow. And what happens is when you have a shear flow, the bubbles tends to be easier to deform because of their shear. And their reason was like they mentioned that because of the shear is they kind of overcome the sum of those what's that called? What does that call? So they overcome some of those like a stress on the surface of the bubble, and then make it to be easier to deform. And then since the bubble is easier to deform, remember that the inner cavitation is a result of the deformation of the bubble. Once it's easier to deform, then of course the inner cavitation will be easy to happen. So that's actually because of that shear flow resulting by the vortex ultrasound that result in the high dosage of the cavitation. Right, and to answer your question about the size, you are right that those bubbles are very small. Typically, the bubbles are 1 to 2 micron in diameter. And the wavelengths we use, so we use 2 megahertz. The wavelength is about millimeter scale.
Right, yeah, still maybe 100 times the difference in terms of overall wavelength.
Right, exactly. But the reason is not because of the ultrasound itself, but because of the shear flow in fluid mechanics.
Thank you.
Yeah. Oh, by the way, I remember it's actually the shear flow actually results in some kind of stress that overcomes the surface tension of the bubble.
Good. I see maybe one last question from Wang Sija. Please go ahead. Yeah, it's good. You're on mute, but we can't hear you yet. If you want to, if it doesn't work, maybe you can type in your question in the chat. Okay, please go ahead. Chengzhi, you will have the question in the chat. So I think Wang Sija is typing.
I just see the word I am typing. That's it. Okay. Oh, so this is the thing. What happens in that treatment? Let me repeat the question first. His question is, so the bubbles are guaranteed by the ultrasound, right? What will happen after treatment? So, he's still typing, but for that part of the question, the bubbles are from 2 ways. One is the cavitation. Because of the ultrasound cavitation that bring the pressure down to the vapor phase such that you form those bubbles. But the other type of bubble we have is we actually inject the micro bubbles into the blood. And the reason we inject those micro bubbles into the blood is because they will actually induce a contrast. Okay. And there are studies of this high intensity focused ultrasound that shows that when you have this high contrast in the fluid, it will make it to be easier to induce the cavitation. And that's the reason why we inject those bubbles inside. So there are actually 2 types of bubbles. One is caused by cavitation, the other is the bubbles we injected. And those bubble sizes are all around 1 to 2 micron. And of course, there are some other type of interesting nano droplet going to the nanoscale, which my student is trying to actually study very interestingly. That we have found some preliminary data showing that the nanodroplet can actually help us to achieve super resolution ultrasound to get into the region with near optical resolution. And of course, my student is trying to test that and then see if we can actually use that to use the ultrasound to see the cells deep into the tissue. So hopefully that can be a successful result and we can actually end up having a very high impactful contribution on the field.
Okay, thank you. Bogdan, I don't know if we have a time limit here, if you want to wrap it up.
No, of course, no. You can take your time and for discussions, but I can stop the videos whenever it needs.
Okay, so I'll ask the audience. So is there any other question for Chengzhi? Let's see. There's maybe a follow-up here in the chat. I think this question about the shear stress to induce the bubble in the vessel. Do you want to take it, Chengzhi?
Okay, so the question is, as he know the bubbles are only generated by longitudinal wave, how can the shear stress induce bubble cavitation in the vessel? The answer is bubbles are not simply just generated by longitudinal wave. As long as you are in the liquid, and as long as your negative peak pressure is low enough getting into the vapor phase, then it will induce the bubbles. It will induce the cavitation. Doesn't matter whether it's a longitudinal wave or shear wave. Okay, and the shear stress is actually you probably need to actually pay attention to the concept here. Shear stress doesn't exist in the liquid. Shear stress is a stress in the solid, and is actually induced through the ultrasound and solid interface interaction. So what happens is we will have shear stress inside the solid, which is the blood clot, but inside the fluid, we can actually induce the peak negative pressure to be low enough such that we get into the vapor region and then form those bubbles for cavitation. Does that answer your question? Okay.
Okay. Anyone else? Okay. Well, if no other question, I'm happy to join me in thanking Chengzhi again for his wonderful talk. I wish you a lot of success. I see the paper was under revision, so I hope we hear from that very soon. Bogdan, I don't know if you want to. Would you want to? We can clap.
Just want to thank you both. Thanks Chengzhi and Mark, and it was great having you.
Do you want to announce who is the next speaker or something?
Just let me have it. The problem is that if I'm opening the other browser, it should be Ornella Matei next week on the premiere.
Okay.
That's right.
I'm trying to open the website as well. Yeah, on November 1st, Dr. Matei on time-modulated metamaterials. Nice.
Okay, guys. Thank you all. Thank you for participating.
Thank you very much.
And, see you soon.
Okay. Thank you, Chengzhi. Bye-bye.
Bye.
Thanks.